Well, it's good to see you again. The last time we were together, we talked about a number of alloys, bronze and brass and steel and solder. And then we talked about some interesting new materials called superconductors. And we saw the Meissner effect, which is a very interesting property of superconductors. And so it's amazing that in just a few lessons we've gone from wattle and daub to superconductors, the ingenuity of man. In this lesson, we're going to talk about magnetic properties of materials and then move into silicon microchips and diodes, transistors, and some applications. Magnetic properties of materials. Now, I'm sure you've played with magnets and you've taken the refrigerator magnet and you try to see if it sticks to various different things, and through your experience you know that it does not stick to wood, it does not stick to your clothing or plastics. The magnet will only stick to certain types of metal. So you've experimentally determined that there are different categories of matter differing in their magnetic properties. And actually we describe these as three different categories. One is called diamagnetic materials, or diamagnetism, which material does not respond to a magnetic field. That would be like plastics and wood and clothing, our own bodies. A second category are paramagnetic materials. Paramagnetic materials will respond to a magnetic field, and that would be many of the metals, and that's why the magnet will stick to a number of metals. And then we have ferromagnetism, which means the material is a permanent magnet itself, okay, like the lodestone, like magnetite. On a molecular or microscopic level, what is the difference of these materials? Well, in most materials, if you remember our discussion of covalent bonding, and mostly the molecules in our body are made of covalent bonding, electrons are paired together to form each bond. And it turns out that when electrons are paired, they cancel each other out in terms of what is called their electron spin. Now, this is going a little bit deeper than we need to go necessarily, but the point is that anytime you have paired electrons, they cancel each other out with respect to magnetic properties. And so things that are magnetic do not have paired electrons. The drawings on the bottom slide refer to those substances which have unpaired electrons and which could potentially interact with a magnetic field. And the top left drawing shows a typical material in which the unpaired electrons are randomly oriented when a magnetic field is not present. But when a magnetic field is applied, they line up and they respond to the magnetic field. That would be an example of paramagnetism. That is, the electrons are perfectly happy to be random unless they experience a magnetic field, and then they will align with the magnetic field. Ferromagnetic material has regions in which the electrons are already aligned. In many cases there will be pockets of this alignment which will itself cancel out so that the material does not appear to be a magnet. But in other cases, if these pockets of material can align primarily in one direction, as shown in the bottom right hand side, then the material is a permanent magnet. Now we're going to switch a little bit, or actually go back to something we talked about in the previous lesson about conductors. And we said that silicon is a semiconductor. It does not conduct electricity very well, but just a little bit. And we're going to now discuss silicon microchips and how they are part of the information revolution based on what is called doped semiconductors. Silicon crystals can be doped by adding small amounts of other elements in place of the silicon in a crystal lattice. In the top example, phosphorus has replaced silicon at one of the positions in the lattice. Now, the key is that phosphorus has one more electron than does silicon. We now have an extra electron potentially can swim through this matrix of silicon atoms, potentially. A second way that silicon can be doped is by substituting either an aluminum or a boron for the silicon. Now the key in this case is that either aluminum or boron, either one, has one less electron than does silicon. This type of doped silicon matrix has places where it is deficient in electrons. Going back to the top, where we have extra electrons, we call this an N-type semiconductor. N for negative or moving mobile negative charge. So an N-type semiconductor has extra electrons. The bottom is what we call a P-type semiconductor, P for positive charge or electron hole. Now, what would happen if you had wafers of two of these different types of semiconductors next to each other? If you think about that a second. For N-type, the electron wants to move. For P-type, it wants an electron to move in to the holes. So the direction of electron transfer between two of these semiconductors, if placed next to each other, would be in this direction. From N to P would be the direction of electron flow. Now this is the basis for the design of diode. A diode is a junction of N-type and P-type semiconductor materials, where the electrons can move in one direction, N to P. That is, it's a one-way gate. So what can happen at these diodes? Well, electrons can only pass in one direction, N to P. If you notice to the right, we have typical designs with three of the semiconductor materials, N, P, and N, or P, N, and P, in which the transfer electrons can go from N to P, but then there's a junction where the transfer is prohibited. So the junctions between these diodes can be gates to either allow the conduction of electricity or prevent the conduction of electricity. One of the things that a diode can do is convert alternating current to direct current, which is a process called rectification. Now, a transistor is a sandwich of these diodes that can be turned on and off through the conduction of electric current. If you have something like an N-P-N junction, current can pass from N to P, but it cannot pass from P to N, unless you have another current that sort of comes in at 90 degrees and tickles the interface, opening the gate, then allowing current to go all the way through. So, a transistor is a sandwich in which other currents can control the passage of current through this N-P-N type of junction. Now, the result is that one can amplify current using transistors. A microchip refers to miniaturizing these diodes and transistor sandwiches. Thousands of these transistor sandwiches of diodes can be placed on one integrated circuit. We find these in our cell phones and computers. And the first transistors were very large, the size of golf balls, but now they are very, very, very small, the size of grains of sand. In this last slide in this session, I want to show how these transistors have become essential in our daily lives. Can you imagine life before flash drives? I can tell you it was difficult. The storage of information has advanced so rapidly in the past couple of decades. It is absolutely amazing. Flash drives, for example, we can now store almost complete libraries on single flash drives. Memory storage devices used in computers and related technologies generally fall into three categories: magnetic storage, optical storage, or solid-state storage. The first example shown here is a USB flash drive, which is a solid-state storage device utilizing silicon microchips. This one has been taken apart so that you can see inside, and you can see the main microchip for storage and then a controller microchip. Basically, these devices work as we described, by having billions of transistors on this integrated circuit, which will store information in terms of electrons being in one position or another position. And we'll talk about binary code in our next lesson. In the bottom of the slide, I show the basic way in which magnetic storage works, and this applies to hard drives and floppy drives. If you remember the first slide of this lesson, we talked about magnetic properties. Well, in magnetic storage devices, something like a layer of iron oxide covers the floppy disk or the hard drive disk, and there is a writing head that moves along the disk, and based on the direction of the current through this writing head, it will produce a magnetic field of one direction or the other, which then aligns the magnetic material on the disc as being either pointing north or pointing south, because the ferric oxide is one of these ferromagnetic materials. So again, we have two orientations, and that will support storage of information using what we call the binary code. Okay, again, we'll pause and ask a few questions and continue on to the next lesson in this chapter on materials.